We've been told time moves forward, and it feels like that, doesn't it? That's just how reality works. But is that really the case? Or just is that the way it feels? Because the fundamental laws of physics don't actually care which direction time flows. They work just as well backwards. So here's the real question. If physics doesn't give time a direction, why do we experience one? Physics, Consciousness and Reality, Dickie Dredd and Nigel Adams. And this is the second part in the Appendix series, so it's the Appendix number 2. And it is called Entropy and the Arrow of Time. Entropy is one of those scientific concepts that has slipped into everyday language, often as a synonym for chaos or disorder. In physics, however, entropy has a more precise role. It is a measure of how many possible microscopic configurations underlie the macroscopic state of a system. A gas in a sealed box can have countless different arrangements of molecules, but as long as the temperature and pressure remain the same, we treat it as a single state. The higher the number of possible configurations, the higher the entropy. This statistical character of entropy gives rise to one of the most profound features of experience, the arrow of time. Thermodynamics tells us that, left alone, systems tend to move from lower to higher entropy. Eggs crack, but do not spontaneously reassemble. Smoke disperses rather than coalesces. Our sense of temporal direction, of past flowing into the future, is anchored in this tendency. Yet entropy also raises questions about the nature of order and meaning. While the second law of thermodynamics seems to imply an inevitable drift towards disorder, we also live in a universe where local order arises, stars form, life evolves, minds reflect. We're here. These processes are made possible by the fact that the universe began in a remarkably low entropy state. That special beginning, often linked to the Big Bang, and we'll cover that in another appendix, has puzzled cosmologists for decades. Why did the cosmos start in a high entropy equilibrium? What hidden principles determined its structure? Stephen Wolfram's recent work offers a striking perspective. In his physics project, he models the universe as emerging from a single computational rules applied to networks of relations. Space, time and matter are not fundamental, but arise from the iterative unfolding of these rules. Entropy is the framework. In this framework can be seen as a measure of the branching possibilities as the computational system evolves. Wolfram argues that many aspects of physics, including irreversibility and the arrow of time, may be understood as a consequence of computational irreducibility. The idea that certain outcomes cannot be shortcut or predicted, only played out step by step. This resonates with the themes of the book. Just as consciousness cannot be reduced to a set of equations, the evolution of the universe cannot always be compressed into a simple formula. Both may be governed by deep rules, but to know what happens next, we must experience it as it unfolds. The irreducibility of computation mirrors the immediacy of awareness. There are no shortcuts to living, perceiving, or remembering. Entropy also connects to our exploration of hidden realities. To us, disorder may look meaningless, but from another perspective, it represents a vast richness of possible states. The apparent randomness of molecular motion contains patterns too complex for us to grasp. Likewise, that seems chaotic in thought or culture may conceal structures invisible at first glance. The festival, the dance, the psychedelic vision, all can appear as noise to an outsider, but within them participants find coherence, beauty, and connection. Dark matter and dark energy remind us, remember we talked about that in Appendix 1, remind us that most of the universe is hidden. Entropy reminds us that even the visible universe is structured in ways that exceed our comprehension. Together they point to a reality where uncertainty and multiplicity are not flaws but features. They invite humility, curiosity, and an openness to possibilities beyond current science. From a cultural perspective, entropy has been taken as a metaphor for decline, decay, or meaninglessness. But there is another way to read it. Entropy as potential, the fullness of what could be. Wolfram's vision reinforces this, suggesting that complexity and novelty emerge precisely because the universe is computationally rich, not despite it. Entropy then becomes less a march towards nothingness than an invitation to participate in an unfolding cosmos that cannot be pre-written. For consciousness, this is crucial. Our sense of identity is bound to memory, to the one-way arrow of time, to the stories that link past to future. Without entropy, there would be no history, no becoming, no growth. What may appear as loss, the dispersal of order, is also the condition for creativity and transformation. To embrace entropy is to recognise that impermanence and uncertainty are not obstacles to the meaning, but its very source. So what this appendix really shows is that the arrow of time isn't built into the laws of physics. It emerges from probability. And if that's true, what we call the past and the future may not be fundamental features of reality at all. Which means the problem isn't just why the universe changes over time, but it might be why we experience change in one direction only. And if that's the case, is time flowing, or are we, or is nothing?